Hello friends, welcome to this video on Cauchy-Schwartz inequality. We will see how to apply Cauchy-Schwartz inequality to problems that involve using them. First, let us get to the statement of Cauchy-Schwartz inequality. Cauchy-Schwartz inequality states that if x and y are going to be two random variables in such a way that e of x square, e of y square and e of xy exist, then e of xy the whole square has to be less than or equal to e of x square into e of y square. First, the condition of existence of the expected value of x square, y square and xy is going to be mandatory for us. If it exists, then the values are not equal to infinity. So that's going to be the statement. So if e of xy we have it to the whole square, then this quantity e of xy the whole square is less than or equal to e of x square into e of y square. In many a case, we may need not the whole square, but rather we may need only e of xy, in which case we would be taking square root of the value with e of x square and e of y square, in which case this will become modulus of the data. So we have positive and negative to extend over, so it is squared on the both sides. On squaring, the square root get cancelled off. So this is going to be your alternative format for your Cauchy-Schwartz inequality. So if you want the modulus of the data, then the modulus will be less than or equal to square root of e of x square and e of y square. Now let's get started with problems. Problem number 1, let x and y be two random variables with mean and variance of x as 4 and 2, mean and variance of y as 2 and 1 respectively. We'll have to find the maximum possible value which e of xy can take. So e of xy's maximum possible value. So we need a value which is not going to be more than that of some quantity. So this value which we get is going to be your maximum possible value. So how to get this? We know the Cauchy-Schwartz inequality. We know that e of xy, the whole square, is less than or equal to e of x square into e of y square. So the maximum possible value it can take will be less than or equal to the modulus of the data will be root over e of x square and e of y square. So our expectation will now be to estimate the data for root over e of x square and e of y square. Now how to go about it? We will use the data which has been given to us, the mean and variance of the random variable x. E of x has been stated as 4 and variance of x has been stated as 2. We know the formula for variance of x as e of x square minus e of x the whole square. Now this variance which has been given as 2, this is my unknown quantity e of x square, and e of x which has been known to me as mean, it is the whole square. So my e of x square can be made as 2 plus 4 square makes it as 16. So this makes it as 18. Now for the second data, what we have is the data on y, mean and variance of the random variable y. E of y, the mean of y has been given as 2 and your variance of y has been given as 1. And we know that variance of y by the formula is e of y square minus e of y the whole square. So this is 1, this is my unknown e of y square, and this is e of y which has been given as 2 the whole square. So my e of y square will be 1 plus 2 square makes it as 4. So this is going to be equal to 5. Now go and apply the data over here. So this will be less than or equal to say root over e of x square on substituted gives me 18 and e of y square on substituted is 9, which is root over 18 5s are 90. So this is nothing but 3 root 10. So the maximum value xy can take is going to be equal to 3 root 10. So this completes the first problem. Let's move on to the second problem. Use Cauchy-Schwartz inequality to prove that the correlation coefficient between the two random variables rho of x comma y is less than or equal to 1. This is a standard property of correlation coefficient that I know that my rho always lies between positive 1 and negative 1. Now we have been asked to show that using your Cauchy-Schwartz inequality. Recollecting the formula for your rho of x comma y is your covariance of x comma y divided by sigma x into sigma y. Covariance is nothing but E of xy minus E of x product E of y divided by sigma x product sigma y. So this is my rho of x comma y. If I am able to show the modulus of this data is going to be equal to less than or equal to 1, we are done. We'll have to apply Cauchy-Schwartz inequality to prove this. Okay. So to go about this way, we are going to take an transformation which is given by u, which is x minus E of x divided by sigma x, and v, which is given by y minus E of y divided by sigma y. If x and y are random variables, then u and v are also random variables. This is our standard normal variate where my E of u will be nothing but equal to, when you take expectation of x minus E of x divided by sigma x. Only this x will get affected because this is already a constant and sigma is already a constant. So you will have E of x minus E of x divided by sigma x, which is going to be equal to 0. So I have E of u to be equal to 0. In a similar fashion, I can also show that E of v to be equal to 0. Now what I want is E of u square and E of v square. So what I am going to estimate next is my E of u square, which is going to be E of x minus E of x divided by sigma x the whole square. It is a minus b the whole square formula. So it is x minus 2x E of x plus E of x the whole square divided by sigma x. Now this expectation, when I take it inside, will affect this x, but this E of x will remain unaffected, this E of x will remain unaffected, and the sigma x, the whole square, will remain unaffected since these are all constants. So expanding about the terms, I will have 2 E of x plus E of x, the whole square, and this is your divided by sigma x square, and this is E of x minus 2 E of x the whole square plus E of x the whole square divided by sigma x square. This is 2 and this is 1, minus 2 plus 1 makes it as E of x minus E of x the whole square divided by sigma x square. Now my numerator E of x square, sorry about the mistake over here, this is x square, E of x square minus E of x the whole square. What is E of x square minus E of x the whole square? This will give me variance of my x in my numerator. And what is the sigma x the whole square in the denominator? That is also my variance of x. So this will lead me to the value called as 1. So I have E of u square to be equal to 1. If I work out in a similar fashion, I can also have this E of v square to be obtained as 1. So we have E of u square and E of v square to be equal to 1. The next line, we move with modulus of E of uv to be less than or equal to root of E of u square into E of v square by our Cauchy-Schwartz inequality. And what do we know about this E of u square which we obtained just now? This is nothing but equal to 1. And what is this E of v square? This is also 1. So what we have is, I'll have to show that E of uv is less than or equal to 1. If I prove that this is going to be equal to my rho, then we are done. Can we start proving it? So what is going to be E of uv? It is going to be expected value of x minus E of x by sigma x into y minus expected value of y by sigma y. Now let us take the expansion of these two terms, which will give me xy minus y E of x minus x y E of x minus this x operated on this will give me minus x. E of y minus of minus makes it as plus E of x into E of y. And the denominator is sigma x, sigma y. Again, keep in mind, E of x will not be affected by expectation, E of y will not be affected by expectation, this will not be affected by expectation, and the denominator will not be affected by the expectation because all these are already constants. So what will the expectation affect? It will affect the first term, E of xy. It will affect the first variable over here, E of y, E of x. This is the second variable where x will get affected, minus E of x, E of y plus E of x. E of y will remain unaffected, so can be cancelled off, leaving you with sigma x, sigma y. Moving to the next slide, what we have over here is going to be equal to E of uv. I have this as E of xy, E of xy minus E of x, E of y divided by sigma x, sigma y. Obviously, we see that E of xy minus E of x, E of y by sigma x, sigma y represents our rho. So what we have shown over here, this is going to be our rho of x comma y. Rho of x comma y. And we have our right hand side by Cauchy-Schwartz inequality to already be less than or equal to 1. So we have rho of x comma y's modulus to be less than or equal to 1, and this proves the required result. I hope you understood the concept of Cauchy-Schwartz inequality and its application to problems. Happy learning. Keep learning.